Everybody doing? Hopefully there you had a little bit of a break and we are all back on track. Okay. Any thumbs up there just to make sure that we're all on the same page? Haley, you're great. Thank you, Mohit. Oh, Nicole. Oh, lovely. Beverly. Oh, you guys are awesome. Okay. So let's get on with this there, and we will hit the other class here. And oh yeah, yeah. Let us. So I'm looking for here, and week 1, 2. Perfect. Sorry, just I'm on another screen here, just getting things going, and I don't know why this PowerPoint is taking forever to load. There we go. Holy crap, man. Let's go. I don't know why it's taking so long to verify it. There we go. Maybe my computer's getting slow. I have to. Okay. Let's go. All right. So here we are. We are now on. Thank you guys for coming there for this this PowerPoint. We are on week 1, PowerPoint 2. All right. This is the last PowerPoint there for week 1. If you haven't seen the previous video there from week 1, then please make sure to go back and see that, okay? But if you're here, sit back and enjoy the ride. Let's have some fun, shall we? Basic chemistry. Now, I know that there are certain subjects there that tend to give people the heebie-jeebies. And mathematics, chemistry, physics, these are... but I want you to understand you're in a good place. You're in a safe place. This is we're not going to go too crazy into chemistry, but there are some fundamentals there that you will have to know. Okay? So again, please don't forget about the textbook. If you don't have it, you'll need it. It will come in very, very handy, especially for your assignments. Did I just say that? Oh no. Yeah, you'll need it. So, please make sure you've read Chapter 1, Chapter 2. I've seen both the PowerPoints there. Let's get on with Chapter 2, shall we? So here we're going to talk about matter. What is matter? Okay. Elements, atoms, the 4 most common elements there that basically comprise most of our body. Okay. Well, we're going to talk about different ways there that atoms can interact with each other. Ionic bonding, covalent bonding, hydrogen bonding. We're going to explain what an ion is and how the body uses these atoms, uses these ions to provide us what we need. Like the whole idea there that Mama always said, Ian, you got to drink your milk because your bones and teeth need calcium, which is very true. Okay? Calcium ions, calcium atoms there within the body. Our body takes this calcium and provides strength there for our bones and our teeth. But what Mama never told me was that no muscle would fire without calcium. No neuron would send messages without calcium. So it's a very important ion. Okay, calcium. We'll get there. Also known as electrolytes. Remember Gatorade? Yeah, which is the biggest scam on the planet. I'll talk to you about that there later. Don't ever buy Gatorade again. It's a scam. Matter. What's the matter? Matter is anything that occupies space and has mass, right? This coffee cup here is composed of matter. Why? Well, it has a mass. And it has a volume. If something has mass, it has to have volume. It has to exist in a 3-dimensional universe. Okay? And matter exists in 3 states. Actually 4, but we're just keeping it easy here. A solid, liquid, gas. Okay, there actually is a fourth. Okay, and it's called plasma, and this is what stars are made of. Okay, but I'm only interested in those three. Two types of change. There is what we call a physical change and a chemical change, right? If I take a log and I cut it in half, what is one half? It's still wood. The other half is still wood. I haven't changed anything. I just cut it into two, right? I haven't changed the chemical properties of it. I've changed the physical properties of it because one log would have weighed 5 kilograms. Now this side here weighs 2 kilograms. This side here weighs 3 kilograms. You've changed the physical properties of it. Okay, you haven't changed the chemistry though. Chemical change. If I burn those logs, can I get my logs back after I burn them? No, they're gone. That's it. Great, somebody's banging something here. Hold on, please. Oh, there's always something going on, eh? There we go. Perfect. So, chemical changes here, these are irreversible, so to speak. All right? And like if you take some eggs, some flour, some sugar, some butter, all these different ingredients there, and you mix them all together and you put them into the oven and you get a cake. Can I get my eggs back? No. That's a chemical change. It's irreversible. Physical change, you can get it all back. Like if I mix salt and water and I make a salt water solution, right? Can I get my salt back? How could you extract your salt from that solution? Well, you'd boil the water. All the water would evaporate, and you'd be left with salt in the bottom. So that's a physical change. Okay, we can get our eggs back, so to speak, with a physical change. Not so with a chemical change. Elements. This is matter composed of atoms that have the same number of positive charges in their nuclei. Okay, trace elements present in tiny amounts, essential for life. So there are, you'll see there when we get into this, the body is mainly composed of 4 different kinds of atoms. Okay, you've all heard the theory there that we're 70% water. Well, water is composed of hydrogen and oxygen, H2O, right? So the majority of us is hydrogen and oxygen. Think about that. All right, but then there are trace elements: iron, iodine, magnesium. We do need tiny, tiny, tiny amounts of this to maintain our perfect homeostatic environment inside. We'll get more into that as we go. So, 4 elements that make up about 96% of the human body weight. Oxygen. So, as I said, we're 70% water. Oxygen's a heavy atom. Hydrogen is not. So, we're about 65% oxygen. Crazy, eh? Carbon. We're about 18.5% carbon. About 10% hydrogen and about 3% nitrogen. Nitrogen there is associated there with muscle. All right, we'll get into that. Interesting. 96% of our body weight is composed of 4 atoms. Crazy. Which just happen to be the smallest unit of an element with that element's chemical understanding. Okay. There are 3 subatomic particles. Okay. There's what we call a proton. There's a neutron and an electron. Okay. Protons, positive. Neutrons, no charge. Electrons are negative. Okay. So protons, positive. Electrons, negative. Neutrons, no charge. So you'll see here, when we're talking about atoms, you know, and every chemistry teacher is a liar. all right, when they first start teaching chemistry. The whole idea there that if the sun was the nucleus and the electrons are orbiting around it like the planets do the sun. You know, it's a great little introductory model and it works. Is it really what happens? No, but for our purposes, let's just keep it like that, right? So you're going to have what we call a nucleus, okay? And here's a better shot right here. We'll have a nucleus, which is composed of protons, okay? Positive charge. There are my protons in the center. This whole apparatus in the middle is my nucleus. And then there is empty space. This is all empty space. And out orbiting the nucleus, so to speak, are the electrons. Okay? And if there are 5 protons, 5 positive charges here, then you should have 5 negative charges here, the electrons. Generally speaking, that's how it works. Neutrons, those are these purple ones here in this diagram. These guys here have no charge. All they do is they add mass to the nucleus. They just make the atom heavier. Okay, so you have protons, positive charge, and neutrons, no charge. That comprises our nucleus. And you'll see there that the charge of the nucleus is positive. Neutrons, no charge, only positive charges in the nucleus due to the protons. And however number of protons you will have, you'll have the same number of negative charges flowing around. So the atom there, an atom is a neutral thing. 5 positive, 5 negative. So you have a look here. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Okay, so I should have the same number of protons in my nucleus. Okay, so that's how an atom works in a nutshell. The atomic number is the number of protons in the nucleus. Okay, so if there are 5 protons in the nucleus, this atom will have an atomic number of 5. The atomic mass, here we're talking about the nucleus itself. It is the sum of protons and neutrons in a nucleus. So your atomic number is only dealing with the protons. Atomic mass, you're talking about protons and neutrons. Okay? Isotope, a different form of the same atom. Same atomic number, same number of protons, different atomic mass. Okay? Different number of neutrons. So, the whole idea here that we can have an atom of a particular element, let's say, I don't know, iron, or I don't know, oxygen, or where there are different kinds of atoms out there of the same element. Okay, and while the atomic number may not change, the atomic mass will. Those neutrons can play a role, and they are the ones that can vary. Okay, so the isotope there, just different forms of the same atom. Hydrogen. There are 3 kinds of hydrogen out there in the water that you are drinking right now. Even if you're having a cup of coffee, the coffee has water in it. The water contains hydrogen. There are 3 kinds of hydrogen out there. There's normal hydrogen there that composes about 99% of all hydrogen. And then there's another form of hydrogen called deuterium. There's actually another form of hydrogen called tritium. And they have different atomic masses, but they're all hydrogen. Okay. The electron shells. Here we get into, when you're talking chemistry here, the magic number in chemistry is 8. Why? I don't know. It just is. All right? It's one of those magic numbers of the universe, generally speaking. Okay? For introductory chemistry. All right? So you'll see there that these electrons that quote unquote orbit the nucleus, okay, which they don't orbit, but I don't want to get into that right now. But they go around the nucleus there, and you'll see there that the first shell it can hold a maximum of 2 electrons. The second and third shell hold a maximum of 8. So if we go back into here there, you'll see that the first energy shell holds a maximum of 2 electrons. The second and the third, which isn't shown here, hold a maximum of 8. All right, and that's what I want you guys to know. The first energy shell, max electrons it can hold 2. Second and third, maximum is 8. All right, where did I go there here? So, number of electrons in outermost shell is critical. Okay, and you'll see here there that the whole idea that the way chemistry works is it's just exchanging electrons. And you'll see here there that these outermost electrons will move, jump to other atoms to create bonds. Like if you look at you can go to, if you Google sodium metal, it's a very dangerous metal. Okay, if you can cut it like butter. It's strange. You can, sodium metal. It's dangerous. If you held it in your hand, the water in your palm would ignite it. Dangerous stuff. Sodium, dangerous metal. Chlorine gas. They used that in World War I, also called mustard gas. One of the most painful ways to die. It's a heavy green gas. They used to put it onto the battlefield, and hopefully the wind was blowing away from your troops and blowing this towards the other troops, and it would go into the foxholes, and it's a horrible element, chlorine. So sodium is a dangerous metal. Chlorine gas is a horribly dangerous gas. But if you mix sodium metal and chlorine gas together, you get sodium chloride. Sodium chloride, also known as table salt, very yummy on your food. So you take something that's dangerous, something else that's dangerous, you mix them together, and you got something there that your body actually needs, sodium chloride. All right, so this is how chemistry works here. And I don't want to get too crazy into it, but we'll get a little crazy. A little crazy is good, no? So, there's your atomic number of protons in an atom. Atomic mass, the number of protons and neutrons in the nucleus. Isotope, okay, an atom there that has the same number of protons, but different number of neutrons. Okay, same element. First energy shell holds maximum 2 electrons. Subsequent hold 8. Okay, so chemical bonding, the whole idea there that atoms can come together to create different things. There's 3 ways that they can do that. There's called covalent bonding. There is ionic bonding. Ion. Interesting. And then we've got hydrogen bonding. Let's have a look, shall we? So, ionic bonding is caused by a transfer of electrons between atoms. So that whole idea of sodium and chlorine, dangerous stuff. And you'll see here there that sodium, okay, has 11 protons, okay, which means there it has 11 electrons. Okay, and what happens there is you'll see sodium here has 2 electrons in its inner shell. It has 8 electrons in its second shell, so it's full and full, but then it has this 1 electron on the outside, and you see it's not happy. It wants 8 on its outer shell, but it's got this one electron just sitting there all by itself. So what happens there if you mix sodium with chlorine? Chlorine has 2 electrons in the middle, so it's full. It has 8 electrons in its second shell, so that's full. And it has 7 electrons on its outer shell. It's not happy either because it also wants 8. So what happens here is that lone electron there on sodium jumps over to chlorine. So now chlorine has 8 electrons on its outer shell. And you see now, and sodium, it lost that third electron shell because when that electron jumped, now that second row, that second orbital becomes its outer shell, and it has 8. So now it is happy. Chlorine, which now has 8 electrons in its outer shell, is happy. And you'll see what goes on here now. See, sodium, which had 11 protons, 11 positive charges, it had 11 electrons, but it only has 10 now because it gave one of them to the chlorine. So it has 11 protons, 10 electrons. So this is a positive ion now. Atom, where the protons equal electrons. Atom, protons equals the number of electrons. But you see, this ion, atom with a charge, lost an electron, jumped over here. So now this is a positive ion, a cation. Here we've got this chlorine here, 7 protons, 17 positive charges. It had 17 electrons, but now it has 18 electrons. So you see there, it has a negative charge, -1 charge. Okay, and you see what we have now is we have sodium chloride. And these guys are bonded. Okay, and that's it. Dangerous, dangerous, yummy. And we can't live without salt. We need it there for electrolytes for our body. I don't know if you guys read this there in the paper there. There was a famous, 1980s actress there. Her name was Brooke Shields. And she was on some movie set or doing something there a couple of months ago. And I guess she wasn't eating properly, or I don't know how it all goes, but she was just drinking too much water and she became overhydrated. Yes, that is a thing, overhydration. Okay, and I just want to make sure there that I am sharing. Am I recording? I don't know if I am or not.